Good morning, everyone. So I see that our panel members are on standby, ready to take the stage. And do you want to tell everyone what the topic is going to be?
Yes, so we're just chatting now that it's quite an exciting topic, and glad to see the room fill up in interest. We've got my iPhone is frozen. I at least know one of the gentlemen personally, Musa. So we've got Musa Malwandla, William Wright, and Vincent Anthony Raja to discuss modern machine learning approaches to actuarial risk management changes from NLP risk discovery to neural optimization. Please let's welcome them onto the stage. Thank you.
Right. Morning, everyone. I think it's been a huge privilege for me in my career, and I think my colleagues will say the same, to see the advances in the investment field that we've had when it comes to the use of machine learning and computers in general. When I think back to sort of my perceptions of what I thought of the profession, where, let's call it at these sort of student career days that Wits used to host, I got the impression that our career was going to be really investment focused, and you'd be able to predict the future and simulate things, and sadly I started off my career in life insurance and pensions, which was terrible. But to have seen the advances first in compute, those of you who started the career at the same time as me would remember sometimes we'd have to set up clusters of computing ourselves, let these things run overnight. But now the profession has moved quite a lot forward, and the technology has enabled us to do that. So today we'll be sharing with you two common problems that we've come across in our sort of careers, and how we've solved them. We believe we've gone some of the way to solving them, and it would be great to get some of your input. So if we think about what tasks today are largely being done by AI, it's kind of interesting, this chart that you see. If I just summarize it for you, I know it's fairly noisy, but the reality is where AI is today, it's really coding work, where we see up to 40% of the workload being done by AI. And the rest of economic activity, and I'd probably guess that investment management is even less than that. It's probably around 5 to 7%. But obviously the point of today's talk is I think there's substantial scope for increased involvement of the technology in investment management. I think it's useful to compare investments to football, partially because we're huge fans, and I think our own career aspirations after investment management are to be part of the data science team. In my case at Liverpool, I think they closed the applications a couple of weeks ago, and if you think I'm joking, just look it up on Google. Yeah. So if you want to use football as an analogy for investments, and I think it's important for us to highlight this. Yes, the use of data, technology, all of the wearables that they put on the players, the huge amounts of ability to filter player behavior, impact on a team, that's all well and good, but at the heart of it, what you're trying to do is put together a portfolio, i.e. a team. You have limited resources, just like you do in investments. You're trying to have a few winners, good strikers, and hopefully enough defense in the composition of the team, i.e. portfolio optimization. But at the heart of it, there's also something that's really important to us anyway, and I thought I'd share that philosophy with you. You still are, when in investment management, investing in companies which are run by people, often selling to people too. So that human aspect is very important to us anyway. I often struggle with youngsters that come and work for us and sort of view investment management and data as these squiggly lines that go up and down, and I need to build predictive models for them. At the heart of it, there is a very strong human element which brings unique problems to every investment challenge. The point of this next slide is really highlighting where we see, let's call it use in the investment landscape. As we can see, when we bucket the industries by broad technology groups, financial services, etc., you can see many peer industries are starting to make tremendous use of AI. So when you look at the technology world, as I spoke to you, a large part of coding is already being used, is already using AI, and I bet you most of you are using tools such as Claude, etc., in your day-to-day lives. Similarly, in previous lives where I've worked, financial services, credit scoring, etc., industry is starting to make greater use, chatbots, etc., of AI. But in my observation, I think asset management is strangely lagging behind, and strangely also making the most comments about whether the AI or bubble is a bubble indeed, yet they're using it the least in their day-to-day lives. Just an observation. Right, so if I was to talk about the areas where I think the industry is going to evolve to, whether we like it or not, and whether one is skeptical or not, I think the first place that one starts when you want to apply AI is on the predictive AI side, trying to predict where share prices and things are going to go. Good luck with that. Then the other components we think actually we've also found probably more success in is on the generative AI side. So using AI to synthesize data, simplify it for us, analyze text. One of the interesting themes that the team worked on and for us is there was a well-known retailer in South Africa, and we were trying to understand the problem that they were having in their stores. We analyzed about 1 million social media comments on it, and were able to synthesize exactly what the problems were, and also be able to trend that. So it's generating information that generally you won't find on a Bloomberg, let's say. Similarly on that, computer vision, I'm sure some of you would have seen demographic analysis using satellite imagery. Those things are becoming more and more prevalent and actually being made available to investment managers to make decisions on. But some of the areas that I wanted to share with you, and the team will share with you today, is really on the optimization and risk management side, where we haven't seen much literature actually at all. So when I talk about standard problems, like for us, the correlation structures between stocks, you do your normal Pearson calculations, but sometimes they're not intuitive. Sometimes there's not enough data. And that's when you resort to a lot of heuristics anyway, sector classifications, etc. So we thought of using, let's call it, the basis of generative AI to help us solve that problem. Look for correlation structures that might not be that obvious or apparent in a Pearson analysis. And then the second problem that we came across, after inheriting all of this compute power, is we built very complex machines to solve portfolio optimization problems. The problem is even using the cloud, it would take a long time to run this and become quite costly. So quite fortunate to work for a tiny company with a tiny budget. And so this team over here has found quite a novel way to solve that problem, but to enable us to iterate a lot quicker so that portfolio managers can make tweaks and just see what the impact on the portfolio risk is without having to wait, let's call it, I think in the past it was a couple of hours, 3-4 hours to wait for a portfolio run to complete. Perhaps I could also share a slide on where we think the impact on AI is going to be, let's call it at least on the insights component of asset management. I actually found this research by Morgan Stanley very useful in terms of where they see the staff components going. So I think the way we see most traditional asset managers today, you have very large research teams, sort of waterfront coverage, covering hundreds of securities, stocks, bonds, etc., feeding up to a few portfolio managers making the decision. And I think as our ability to process information far more efficiently and also manage risk more efficiently using these tools, we see that the pyramid becomes a lot more narrower, which hopefully will also lead to, let's call it more cost-effective approaches, but also more rewarding career path. So you don't have this, huge intake and have to get rid of people by all sorts of corporate politics, etc. And I just think it'll be a more rewarding career once we have a more efficient path to portfolio management decisions. So as I've mentioned, I'm not going to repeat this, but the two papers that we'll be talking about today really are on correlation structures, and the second is on optimization, and I'll hand over to my colleagues.
Great. Thanks very much for the introduction, Vincent. So my name's William Wright, and I'm the lead data scientist at Differential Capital. And today I'm going to talk to you about some work that we've been doing at Differential that will hopefully make you rethink a little bit around portfolio diversification and its implications on risk management. So the core research question that we were trying to solve at Differential is, how does one actually systematically incorporate sort of the rich contextual and textual information in corporate text like corporate disclosures and things into actuarial risk frameworks? And you might be thinking to yourself, well, we already do that. You've got teams of analysts that will be poring over these documents, poring over news, and what they read informs their views and their opinions, and that information will be encoded into the models that they build, right? Well, the problem with that is that it's not systematic and it's not consistent. And very often, there's also an element of bias that's involved in that process in and of itself. So there's a big gap for trying to do this process in a systematic way without bias. And there's also a scalability aspect here. The resources that you need to sort of cover 1,000 of stocks in a similar or in such a fashion ends up, sort of growing exponentially, and you always have that issue of consistency and potential bias throughout that process. So there's a missing systematic framework for this. And what we feel we've been able to do with our research is build out a framework that enables us to combine semantic analysis with a mathematically robust framework using shrinkage estimation that allows us to encode not only the historical information and correlations that we see in price data, but also the forward-looking data that's encoded in documents like corporate disclosures and financial reports. So just to kind of illustrate the problem a little bit, I've got a chart on the slides behind me that show the average correlations on the JSE over the past 20 years. And you'll see, a variety of spikes that occur throughout that time period. And surprise, surprise, there's a high chance that those spikes, correlate with crises. A particular one being the COVID-19 pandemic, which you can see quite obviously on the slides. And one of the sort of big issues with correlation analysis as it currently stands is traditional methods capture previous relationship but miss potential future vulnerabilities, right? And when you are, say, building your portfolio, trying to build up a diversified group of assets, and manage your risk, very often that portfolio is built off of a view of what happened previously. And in the case of, say, the COVID-19 pandemic, where you have your portfolio and everything's looking great, then a single event occurs that basically causes all of these diversified players to move in tandem, and your diversified portfolio collapses, right? This is because of a phenomenon referred to as sleeping correlations that sort of present themselves during these stress periods. And maybe I can, improve on this explanation with an analogy. And as Vincent mentioned, we love football at Differential, so it's only natural that I talk about a soccer match with you guys. So let's imagine you're watching a soccer game, and you've got your players that are all distributed about the field during the possession phase. Your defenders, your midfielders, your strikers, they're all sort of moving independently of one another. Their movements and their positions are seemingly uncorrelated, right? Now, say a corner kick is awarded. all of a sudden there is a shift in the movements and positions of the players. Defenders move into the box to protect the goals. Other players move around to assist with defending. Their movements become correlated with one another in response to a given scenario, right? That would be an example of a sleeping correlation. It already existed, but the introduction of this new set piece caused it to sort of awaken. And if we provide a more tangible market-related example, so you've got two mining companies. They both mine different commodities, and they're both positioned, at different points geographically in South Africa. That could be a compelling diversification opportunity, right? Then say Eskom load shedding hits again, and both companies are affected because of their need on stable electricity supply. Your sleeping correlation's been awoken, and that information would not have been captured in the historic price information. So before I talk a little bit about the detailed framework that we used to try and incorporate or improve on this risk framework, I'm just going to talk a little bit about one or two technical concepts. The details are not all that important. Similarly, there's not going to be too many formulas. The math's not all that important. But what's important is the intuition, right? And the sort of fundamental concept is this idea of an embedding. What is an embedding? So it's a mathematical representation of an object as a vector in a higher dimensional space, right? And it doesn't necessarily need to be any particular type of thing. It can be words in the context of text. It can be sentences. It can be paragraphs. It can be assets, right, in a financial portfolio. So the sort of important thing to take away from here is if you can think of it as coordinates on a graph if you draw in 2 dimensions on a piece of paper, right? Except instead of X and Y coordinates, you can have multi-dimensional coordinates that capture information about this object in this higher dimensional representation, right? And the big important takeaway here is just like, you can have 2 points that are close to one another that are similar in that graph context, 2 points in this high dimensional space that are similar to one another, or are close together to one another in this high dimensional space are similar to one another. So as an example, I've got sort of an example from a traditional, shall we say, text processing type problem, where we have words like king and queen. And if we have a look at the numbers that compose the vector of those words, they're similar to one another. They're close together in meaning, and they're close together in their representation. The exact same idea can be applied to financial assets, where we can have, say, 2 stocks that have got similar returns and risk profiles are close to one another in their embeddings. So what these embeddings do is allow us to preserve relationships between these objects while allowing us to also perform mathematical operations on them, adding, subtracting, multiplying, so on and so forth, right? And now I'm going to talk a little bit about how these embeddings fit into the overall framework that we built to try and encode this contextual information that's in this text. So we start off with, corporate disclosures, financial reports that companies publish yearly, a big chunk of text, right? That's all been sourced, collected, and standardized into a format that we can process programmatically. And this is, I think, the sort of the key innovation that we've developed here is we use a generative artificial intelligence model, in this case specifically a large language model, to generate thematic narratives from that text, right? Themes that will be useful in the context of performing our correlation analysis further on down the line. And we use our embedding process and to build embeddings out of these thematic narratives for each of these firms, right? So now we've got these mathematical objects that are related to these narrative themes that have come from the corporate disclosures. We then combine that with our historical correlation matrix using a shrinkage estimation. So well understood mathematical technique that's robust, and we now have this object that we can use in our optimization, our portfolio optimization process further on down the line, right? Now let's drill a little bit into that generative AI step over here. So remember, we start off with this huge body of text with all this information that has sort of the forward-looking components in the text is of paramount importance to us, right? And it's the stuff that businesses would want their investors to know. We start off by deciding on a set of themes that we want to extract from this data. And for the purposes of this research, we focused on 3 themes. The business model theme, so how does this business generate its revenues? What is its competitive advantage? So on and so forth. A geopolitical theme, what sort of policy risks would this business be susceptible in the future? What sort of geopolitical events could cause a problem for the company in the near future? And an ESG theme, so what sort of sustainability vulnerabilities exist within the business. These aren't the only themes that you could explore. You could definitely include more, include less, vary the ones that you have. These are the ones that we chose for the purpose of this analysis. We then use a generative AI. In this case, for this research, we used OpenAI's GPT-4 to perform this analysis, and using a robust prompt engineering framework, got the model to distill that information from the text and build up those chosen narrative themes. And I've just got an example of what a prompt might look like in this case, but it's important to note that this is also an iterative process. It goes through many cycles, and there need to be guardrails in place to ensure that you've got consistent results being generated by the model that can feed downstream processes, right? And out of this process, you would get, say, a few paragraphs of structured text in a consistent form coming from the model that relates to those given narrative themes, right? Now, I just want to talk a little bit about the shrinkage estimation part. There's only like 4 formulas in this, so don't stress. Effectively, we combine our historical correlation matrix, which we've built using historical price data, with this matrix consisting of embeddings from our semantic analysis using an optimization or an intensity parameter, lambda, in this case. And I also wanted to stress here that this isn't an arbitrary, assigned number. It's not an ad hoc process. It's an empirically optimized value that we derive through a cross-validation process that ensures, stability throughout subsequent work in the process. And it also ensures positive semi-definiteness for our portfolio optimization task. And I think a big component of this is that this is not replacing your current optimization processes. This feeds into existing processes very naturally, and that's part of the reason why we included, we went about designing it in this process, is that it's a plug-and-play solution that improves your risk management processes and frameworks. So, as far as a results comparison is concerned, I'm just going to talk about the risk measurement metrics that we included here. So marginal risk contribution, so how much each component in your portfolio contributes to your overall risk, effective number of bets, your measure of your total diversification throughout your portfolio, and your standard tail-end risk measurement value at risk at 95%. So just a comment around the data that we used throughout this research. We took the sort of financial reports and disclosures from 125 JSE-listed companies across multiple sectors to ensure that we weren't cherry-picking a sample. We were getting broad representation of the market. As far as price data, we took 2 years worth of historical data, approximately 500 observations for each company, so that we've got enough data to ensure stability, but at the same time, the data is recent enough. We're not encoding stale information in our analysis. And also, throughout our validation process, we want to ensure that whatever we're seeing is not an artifact of a given correlation framework. So we not only used Pearson's correlation, we also used Spearman's rho and Kendall's tau, to cover your rank and your tail sort of analysis as well. And this leads us to talking about the results. And I think this sort of slide is quite important to go through because it captures, in my mind, the core of what we're saying about sleeping correlations and hidden risk. So on the slide, you're going to see 3 heat maps, each heat map corresponding to a given narrative theme that we used in our research. So business model, geopolitical, and ESG. The rows in the heat map are the traditional sector classifications that you'd use, so basic materials, financials, technology, so on. The columns in each is a narrative cluster that was assigned by the framework, right? It's important to sort of note that this is not anything that we decide upon. This is clusters that are assigned by the model, so there's no interference there or anything like that. And I'm going to specifically focus on the business model and the geopolitical heat maps, right? So if we have a look at the business model heat map, we can see that if we look at basic materials, we've got 19 companies that are all sort of concentrated in our narrative cluster number 1. And when you think about materials as an industry, that makes sense, right? There's not a lot of, or resource companies and mining companies will generate revenues via a similar method. There's not a lot of variation there, so that makes intuitive sense. And we can say the same when we have a look at financials, right? 21 companies that are clustered in our narrative cluster number 5. Makes sense. Business models don't differ drastically. There will be variation, but not a huge amount on that specific narrative angle. Let's now focus on the geopolitical clustering, which I think is where we see things start to change up a bit. If we focus on basic materials, we can now see a spread in how different firms are influenced by different geopolitical narrative themes. Even though we have 19 companies that all sort of are similar in terms of business model, they could all be susceptible to different forms of geopolitical risk, right? And if those different if those levers are pulled, different companies could be affected at different points, which could affect your state of your portfolio's diversification. Similarly, if we have a look at narrative cluster number 5 in geopolitical clustering, you'll see that every traditional sector in some way has firms in it that will be influenced by that particular lever. So if that lever gets pulled, basically there will be firms in every single industry that will be drastically affected by it, causing huge implications for risk and diversification in your portfolio. Let's talk a little bit about the actual risk metric results. So if you see the chart on the screen now, that shows the effective number of bets comparing the historical correlation only on the far left, and each of the other charts showing the inclusion of the various semantic correlation analysis across each of the themes: business model, geopolitical, and ESG. And on average, we see a 75% reduction in the effective number of bets. So I just want you to let that sink in for a little bit. We went from 15 previously down to, in the case of ESG, 2, right? And this is consistent across your correlation metric that you use, Kendall's Tau and Spearman's Rho. We see similar sorts of results, right? So this is another indication that there's a huge impact to your portfolio's risk by taking these correlations into account. Similarly, if we have a look at our tail risk assessment results, we see an increase of 62% in 95% value at risk on average when we include our semantic correlations. Similarly, we see a drop of 43% in our Sharpe ratio from 2.5 to 1.4, roughly. And our portfolio volatility goes up by 79% from 7.8% to 13.9%. And I think what's important to sort of stress about this work is that we're not saying that your portfolios are bad. We're not saying that the returns are rubbish. What we're saying is that these correlations already existed there. And if you are relying purely on the historical information without including the forward-looking narrative information, you are potentially building overly optimistic portfolios that don't capture the real reality, the real risk reality. And this framework that we've built helps to sort of uncover that and bring those relationships that it sort of exist to light. The sort of real value we also find is the fact that this doesn't require you upending your entire portfolio management and building process. It plugs in to an existing framework that basically allows workflows and work streams to be continue as usual. But this isn't the only area where we've done work on AI and computation in the portfolio optimization space. And I'm going to hand over to my colleague, Dr. Malwandla, to talk us through the work that he's done involving transformers and portfolio optimization, taking times from potentially hours, sometimes days, down to milliseconds. Thank you very much for your time.
Good morning, everyone. So I'll be speaking very quickly on a separate piece of work on optimization. So the idea here is, at the moment, machine learning models, the way they are applied, are learning to rank algorithms. So they rank assets. What we are proposing here is a slight paradigm shift to learning to optimize, which is a slightly different way of thinking about it. So the idea here is, again, to carry on the soccer analogy, is if you think about a soccer game, you have to deploy continuously, change players based on the state of play, right? And you want a model that can do that quickly. You don't want an analyst, a football analyst, to go and map it out. This guy is injured, let's see who best. An experienced coach will figure that out dynamically from all of the years of experience. So the idea is, can we train a model to have that kind of understanding of diversification and risk management so that it can actually optimize a portfolio? And ultimately what that allows you to do is to do end-to-end modeling. So you're not just training AI models to rank assets, you're also constructing portfolios at the same time, which is actually something that's not currently done in any of the prevalent frameworks. Okay, slight deviation from the soccer analogy. If we look at basketball, if I were to ask most people who's the greatest basketball player of all time, they'll probably say Michael Jordan. And the way they think about, and maybe some will say, LeBron and so on. They are thinking about it in terms of learning to rank who are the best players. But what they don't think about is, for instance, Michael Jordan had never won an NBA championship without Scottie Pippen in his team. So the fact that you have Michael Jordan in your team actually means nothing if you don't have Pippen, right? That's what it's telling. And this insight is often missing in portfolio management. You might pick the best assets or have the best AI model to pick assets for you, but it might end up neglecting assets that are actually useful to help the other assets in the real world. So that's the idea. Okay, so the specific research problem is firstly computational, is that if you run an optimization algorithm, if you think about it, in the MSCI world, you have 1,500 assets. So if you run an optimization algorithm, you're trying to solve Lagrangian multipliers, if you still remember, and across 1,500 assets. It takes days in some cases, right? So how do we solve that? Firstly, the computational bottleneck. And then the other one is the point I was making earlier, is that the prevalent approach is learning to rank, not learning to optimize, which is a slight, a very fundamental paradigm shift that we wanted to explore. There are then other ways of applying this research, which I'll speak to at the end in more general terms. Okay. Now, at the core of what we're trying to do here is, if you think about traditional optimization, you will have a set of expected returns, volatilities, and a correlation matrix. You then run it through some sort of solver, using Newton-Raphson or some other algorithm to find the portfolio with the highest utility, right? And that's the computational problem. So there's a mapping. The mapping theoretically exists between input and output. In other words, input being all of those parameters, output being the optimal portfolio. But in order to get from one to the other, it takes hours or days. So our idea is that because the mapping exists, we can learn the mapping, right, iteratively. So we can build a model that actually knows. So it's no longer an optimization problem. It's learned the function that maps A to B. So it's a shortcut through all of the Lagrangian nonsense and so on. Okay, so and that's what's illustrated in the picture on the left is traditional, it's iterative, and we are just building a model that cuts through all of that and learns the problem. Now, jumping to how it actually works, it's using the concept of a transformer. It's a transformer architecture. What's a transformer? It's the AI architecture that powers large language models, GPT. A lot of the large language, so the T in GPT is transformer. Now, how does it work? Normally, it's a token-based, so if you have words in a sequence, it's trying to predict the next word in that sequence. If we then delve in deeper, for an audience such as ourselves, you can think about it in simple terms as a Markov chain's older brother. So how it works is, if you think about the picture on the left, a Markov chain is what in language modeling would be called a bigram. You are saying, let's say you're trying to complete this sentence, the cat sat on a mat. The first word would be the, and you are then using a Markov chain to figure out if the current state is the, what is the probability that the next state is, a cat, or, and obviously you can see quite quickly that if you use that kind of model, it will actually produce nonsensical results, right? You can't model language by looking at one state at a time. You actually need to look at, it's not a Markov, it doesn't satisfy the Markov property. Now, the idea is then with a transformer, which is a picture on the right, is it still is kind of a bigram at the core of it. It's looking at the current word and trying to predict the next one. But there's this thing called attention, which is effectively trying to smuggle in information about the past data, right? So using the embeddings that William was speaking about. Each word has a representation, and then it uses that to smuggle information to the current state and try and predict. So in fact, the transformer itself should be a very powerful concept within our domain, because it replaces the archaic idea of a Markov chain. Now, if you then look at it, what is this attention thing trying to do? Attention is, so if you think about words, each word would then have an embedding, as Will spoke about. Each embedding encodes the meaning of a word. So this word means dog and cat and king and queen. It sort of figures out what the word means. That's what it encodes in that vector. Attention then allows the model to find similar words. So if the current word is cat, it goes into the past and finds words that are useful in making the next prediction, given that the current state is cat, using that embedding matrix. So it's a sort of a similarity, finding words that can help you figure out the future. But the idea is, in the same way as you have embeddings for words, you can have embeddings for assets or for anything. So in our case, we are looking at assets, so you can build an embedding for an asset that tells you the essence of a gold stock, or a share held in First Rand or some other company. So that's the idea. Is although this is a language modeling task, the mathematics is the same that we can apply to other concepts. So now, just very simply, in natural language processing, the way you would normally build these models is for 3 types of tasks. So the first one is next token prediction. In other words, what is the next word in a sentence? That's how GPT works. It's predicting the next token. There's masked language modeling, where you can replace a word in the middle of a sentence and it figures out what's missing. And then there's sentiment analysis, where you can figure out the entire sentiment. Our approach in this portfolio problem is similar a lot more to the sentiment analysis, in that we have a collection of assets, each one having an embedding. They all listen to each other using that attention mechanism, all in service of trying to create the optimal portfolio, right? To create a set of weights that will optimize the utility of the portfolio, right? So that's the core. Now, the first sort of innovation we had to think about is, how do we create these embeddings? There are 2 ways you can create an embedding for an asset. So that numeric representation of an asset is, you can build a model that learns this embedding. The problem is that takes a lot of time. The other way, which is how we did it, is we used correlation matrices themselves. So if you take a correlation matrix, it could be a historical correlation matrix, or the kind of correlation matrix that we spoke about earlier. Is you deconstruct that into factors, effectively using eigen decomposition. So you now have a vector that encodes the relationship between assets, and then you also add in information about asset features like expected return, volatility, and so on. Now all of a sudden you have this embedding vector that represents not just how assets relate to each other, but any views you have on those assets, and that forms the input into your transformer, right? With all of that having been said, we then build a transformer architecture. It's similar to this. I won't bother you with some of the details. It is quite intricate, but the point is what goes into our model is expected returns, volatility, and a correlation matrix that's then translated into an embedding vector. What we then do is to train this model to solve a problem, right? Now, this is just some of the math on eigen decomposition, which I won't go into, but it's effectively taking the correlation matrix and figuring out the factor loadings. In other words, how do assets load to different factors, and therefore which ones are similar or different to each other. The other innovation here is, in order to train a model, you need data, right? And in our case, we would have needed data on optimal portfolios in the past. So we would have had to optimize millions of portfolios and then feed it into the model. It turns out we don't have to do that. We use self-supervised learning. So we started with a blank model that doesn't know how to allocate a portfolio at all. It's never seen a portfolio. We then built the embedding matrices for different assets. We then gave it synthetic problems. In other words, different vectors for expected return, correlations, etc. And then all we told it is the reward function, which is optimize the portfolio using the quadratic utility function, for instance. Now, over time, it then sort of starts to learn on its own, right, using these synthetic problems. Now, we shaped it as a curriculum. So earlier on, we give it a very basic problem with all of the assets having the same expected return and volatility. The only thing it can learn is the correlation structure. And then over time, we then started to add more and more complexity to the problem. So you might think about it as grade 1 versus grade 12. We are slowly making the problems more difficult. Now, that's all we did, right? Built architecture and allowed the model to train itself. And quite quickly, after about 2 hours of, probably less, let's say about 2 hours of training, it then learned to figure out diversification on its own, like how do you allocate assets. So in other words, as the risk aversion parameter increases, it knows how to allocate, exactly as you would expect, right? And that's, the picture on the graph, if you look at the bar chart, it's telling you the kinds of things that it's considering in an optimization, exactly as you would think. Correlation, the more correlated assets are, the less they should, feature in the portfolio. So it's learning, it works. Now, the other observation was how well does it actually operate? So if you think about, those two problems, is computational efficiency. In a portfolio of, let's say 500 assets, as you scale up, the computational cost of running a traditional optimization increases exponentially. Our model is linear, right? So in other words, as you add assets, you're only adding a linear amount of additional computational time, whereas the traditional approach is exponential growth. And in terms of computational efficiency, it's not that inefficient relative to. So here we only trained for a few hours, and it was a fairly small model that could train on a laptop. If you want more, computational power, obviously you can train on a GPU, and a larger and larger model would obviously then, solve the problem a bit better. But the point is, this was achieving about 99% efficiency relative to a traditional optimizer, and that efficiency increases as the problem gets larger. Right, so this particular model can take care of different asset size. So whether it's 50 assets in a portfolio, 1,000, it can solve it all the same, and it gets more efficient relative to a traditional optimizer the larger the problem becomes, right? So that's the idea. Now, the way you would think about this now is we've given this model synthetic data, and it's very similar to how we are all trained as actuaries. Is in CT levels, you are looking at abstract synthetic problems, solve this, mathematical problem, and eventually you go into the real world where you're dealing with real problems. We are thinking about it in the same terms. Is we've trained this model on synthetic data. What would it look like in the real world? We then take the same, we would call it a pre-trained portfolio allocation model. We now want to apply it to the real world. When you apply it, you can either apply it as is or start to fine-tune it, right, so that it actually understands the real world better. So that's what we did. We applied it to the JSE All Share, and here we were taking data from the past, so and estimating a correlation matrix. We weren't doing this fancy stuff that Will was speaking about, just normal correlation matrices and saying, solve this optimization problem and construct a portfolio today, and then we want to see how that portfolio performs. So the base model without any fine-tuning was outperforming. The amazing thing about this model, for the lack of a better word, is that you can now link the model to, so at the moment, the way I've explained it is the inputs into the model are preset. In other words, it's expected return, it's volatility, and so on. How you could do it is then add features like asset momentum, any feature that you believe would influence performance, right? And then actually train the model end to end. So it first ranks the assets and then allocates, rather than just allocating. So that's the other model there, the one that performs better is. That's a model that's then not just the pre-trained transformer, it's one where we've now trained it on features, right? And again, here the performance is actually not that meaningful. The point here is that you have a framework that can do this, and the better your input features and so on, the better the model can perform in real time. Now, this is a paradigm shift in our view because, if you think about traditional optimization without ML, it's analysts or the portfolio manager will present, the optimization team with a set of beliefs of expected return volatility and so on, and then run an algorithm to solve it, which could take hours. The current machine learning paradigm is to use the AI to rank assets. In other words, which assets are good and bad. And then the optimization happens traditionally. And then what we are doing here is doing that whole thing end to end. And the problem, the nice thing about this is you can now solve more neatly the problem of Michael Jordan versus Pippen. Is that if you just use a ranking model to pick your assets and then assume that will automatically produce the best portfolio, that might not be the case. Whereas now we're training end to end to pick assets that actually work well together, which is why we believe it's a paradigm shift. Now, the other thing is, here we've been speaking about portfolio analysis. The architecture is actually more general. It can be applied across the board, whether it's in the actuarial space or outside. Here are three quick examples before I wrap up. The other one is, so the first one is what we call learning to win, is we've been using sporting analogies the whole time. Is suppose you're a gambler and you want to figure out who will win a particular game. You can build a model like this using the exact architecture that we've designed. Is each player will have their own embedding matrix, and if you have historical data on win rates, in other words, which team won and which players were in the team, you can train a model to figure out the embeddings of each player, and therefore the likely winner and loser in a particular game given the formation and the people on both sides of the team. That's an example, very simple, that you could use this for. The other one, which is more a generalization, still the same architecture. This we actually built a dummy model, it's on actual data to prove this example. Is if you think about yourself as a professional, you have certain skills. What is the value of your skills in a portfolio? So if you think about portfolio management, you as a professional, the assets you have are your skills, right? You can actually apply a valuation. So how we did this is we use labor market, so income. So we take job postings, the salaries they are paying on the jobs. Those are revealed preferences for what the market prefers. Then you are training the model to figure out how your skills as assets contribute to each other. So and it's not, so if you have a skill in pig farming, and you're an actuary, those are actually not adding value to each other, right? So it matters how the skills are in the portfolio. So again, there are no frameworks that do this in the traditional statistical framework. So again, this is just another example. And then the last one quickly is that, so aside from the idea of resource allocation, there's a more fundamental problem that excites me a lot more, is this problem of mapping between input and output, so cutting out the middle part of optimization. So this links to the there's a problem in numerical in numerical maths called computational irreducibility, is that certain problems, the only way to know the answer is to work through numerically. It turns out that that might not be the case, in that if you train a model, it cuts through that work that in the past was assumed to be necessary, right? And you can apply this across the board, not just to portfolio optimization, to any other problem. You can train an AI to sort of solve these problems dynamically. With that mouthful, I'll then just maybe conclude with a few remarks. So clearly, as Vince mentioned, within actuarial risk management, there are a lot of ways of applying AI. And I think the way we've been thinking about AI is, it's through, it's ChatGPT as a coding agent, and we think about it as amplifying risk rather than reducing risk. But clearly, there are quite a few ways of applying these techniques. And it applies in every domain. And I think this piece of work opens up a lot of opportunities for further research, which, if anyone wants to reach out, we're happy to collaborate. And then I think before I open for questions, there are a few polls. So quick question, if you have your ESSA apps. The first one, if we just bring it up, was on AI application in the next decade in actuarial work. And here, this is actually quite important because the way things are evolving, one interpretation might be adapt or die, and the other might be, well, this is all a bubble and it will go away. So it would be interesting for us to sort of figure out where the audience sits on this, and we'll gauge where we are in a year. Or maybe in the interest of time, maybe we're disrupting the network here. I don't know what's happening. We can just jump to questions, perhaps.
So what we can do is we can take questions now, and then as the results come in for the poll, you can analyze those results afterwards. So just checking if there are any audience questions so far while you participate in that poll. There is a question over there. We've got a microphone for you.
Thank you for the talk. So my question with regards to the semantic analysis. So and I did see that one of the models that you're using is the GPT models. So then have you done a comparison to look at how your results would perform if you used a different LLM?
Hello, is this? Yes, thank you very much for the question. So we didn't compare different model frameworks in this specific case, but we don't necessarily anticipate there to be too much of a difference between using different LLMs for this task, because the actual sort of core task we're asking of it is a simple summarization, and basically through an iterative process, you can basically get standardized results irrespective of your architecture. So we don't anticipate there to be a shift, and it's also a matter of cost, so you can use a very expensive model to infer on the current generation GPT-5, or you could use a much more cost-effective model to achieve a similar sort of output.
So for those of you who want to understand how to participate in the poll, so all you need to do is go to the app. I see many of you have the app open. Then you're going to go to this particular section, which is investments, and you're going to click on that. And then it's going to have three sort of tabs. One says information, which tells you what this panel is about, but then the other has vote. So if you click on vote, you will be able to see the question that reads, AI's impact on actuarial work in the next decade will be, and those are the options. So you just click on this particular session, which is investments. You will see a little section there that says vote, and that is how you're going to vote. So to test it out, we're going to let Ricardo vote. You get to pick what you think, and you can select your option there, and we'll see as it comes through.
I thought voting was private.
I'm not looking, I swear. Okay, we do have a question here. Do you have a microphone? There.
Hello, Nicholas Bezuidenhout from WITS. I'm sorry to do this. I've got sort of one comment and two questions packed together. I don't know if that's all right. My one comment was it's to do with the semantic analysis. The sensitivity factors, I suppose, by the analysis that you're doing are inherently based on historical information. Is that maybe if you could just address that? How does one know that that's going to be the case sort of going forward? And then I want to know if you could give some examples on some of the narrative clusters. You know, if the model generates this, how can one intuitively understand? I mean, do you have some intuitive examples of what the groupings were for business model or geopolitical exposure? And then my last comment was, you know, what businesses say and what they do, you know, compared to their financials are often very different. And if you're basing analysis on that financials, I suppose a portfolio manager or an analyst might be able to have some way of determining that the actions on the ground differ to what's being said in the financials. How can that be factored in? Thanks.
Let me start with the last one. So I think the reason we chose the annual reports is it might be easier for people to try and replicate what we've done. But what we would recommend is that if you had access to stockbroker research and your own internal research on companies, that you feed that in as well. Because exactly to your point, not only what companies say, there's also a huge variance in the way they approach risk management and describing their own businesses, which I think you could probably enrich that by adding further sources to it. So I think it's the framework that's more important than the specifics that we've done here. Yeah.
So what was the other question?
So the one was about the sensitivity factors. Are they not based on historic information? Okay. And then just some examples of the narrative clusters.
Yeah, so examples are in the paper. So there were several. I mean, in the paper we spoke about, for instance, how, you know, so there were in large part the clusters align with historical data, which is what you would expect. Banks do tend to correlate, and they have the same business model, and you know they're exposed to the same ESG risks. But what's more interesting for us is cases where it disagrees, where it differs from traditional intuition and historical data, and I think those are the most interesting ones. So there are several case studies in the paper. I don't remember some of them. I think Richmond was another, which you would. I think Richmond doesn't. It historically correlates with consumer discretionary companies, but from a business model and a geopolitical analysis perspective, it differs entirely, right? So, and in fact, what it means, so in practice, how you would apply a framework like this is you want your portfolio to generally not be over-indexed in any one theme, right? Or the effective number of bets across different themes should be high, because it means that regardless of which type of event awakens, you still have the same fundamental diversification. And then I forget now again the other.
It's just about the nature of it being based on what's happened in the past, based on your your calibration of those sensitivity factors. I mean, how does it sort of assess that? Because surely it's looking at these themes and saying, okay, well, there were commonalities in these themes. This then influences the historic correlation.
Yes.
So there's an assumption that relationship's still going to play out going forward.
Yes. So the way we were thinking about that is as opposed to what. So the problem is with the current approach, which is historical analysis, the well-known problem is, firstly, those are unstable in themselves, historical correlation. And the other problem is that you have ill-conditioned historical matrices. So if you construct a correlation matrix on the past, it tends to be ill-conditioned. If you use it for optimization, it won't work anyway. So the best way to apply this would be to set the lambda parameter so that it's calibrated to the past. So in other words, you would train it so that your correlation, so in other words, for instance, you would go back to 2021, use semantics as at that time, and then see whether, what level of correlation best leads to the best predictive correlation matrix, right? So in other words, if I were to construct this blended correlation matrix today with a particular lambda parameter, which lambda parameter best ensures that my current correlation matrix is a reflection of the future, right? That analysis we didn't do, we just used the current static one. But in a comprehensive implementation, you would need to go and perform a historical analysis on what the best lambda parameter would be for predictive purposes. Yeah.
Okay, we've got another question, 2 more questions. And a question there. So we'll try and get the microphone. Let's get to you, sir, because the microphone is closest to you, and then we'll take your question next.
Hi, everyone. Thanks for the talk. Just thought to ask for more clarification on the effective number of bets, and what does it mean to be a high number or a low number? If I Google it, it says a high number is better diversification, but you're indicating that lower number is better. So I'm just trying to understand that.
So no, that maybe was a miscommunication on my part. So we went from a portfolio with a high number, effective number of bets when we just incorporate the historical context and the historical correlations, and that appears to be positive. You've got a well-diversified portfolio, but when we include the semantic correlations, we see the effective number of bets dropping.
Okay, so the portfolio is the same, but the method of analyzing it is different. And once you use your method, you say it's a worse portfolio.
No. So it's a lens. So we didn't re-optimize the portfolio. We are saying if you look at the portfolio using this lens, yeah.
Maybe we can ask both questions and then field them at the same time. Are you ready with your question?
Yes, I am.
Yes, and then you can pass the mic that side. Thanks.
Okay. Cool. Thank you, guys. So I suppose I've got just 2 sort of, I hope they're related questions. But the first one is, so both of them are on the second paper. In terms of the mean variance optimization approach, that sort of is a sort of closed form solution type problem, right? So I imagine it would, if you've got expected returns, variances, correlations, and the likes, and you feed that into an MVO and you get weights on the other side, isn't that always closed form in a sense? Unless you start perhaps adding other constraints, so to speak, and then perhaps you start to get a sort of non-linear problem there that you perhaps might require some iteration to solve for the weights. But if it's just expected returns, variance, and correlation, then perhaps, is it true that you wouldn't then need to have the sort of neural network sitting in between there to have that fast mapping from inputs to outputs? So that's the first one. And then the second one is I'm interested perhaps in the objective function. So, what exactly is it? Is the network learning here in terms of what it's trying to optimize for? So, is it trying to maximize, for example, the information ratio, or is it trying to, or can you give it a target level of alpha and then train it on saying I want my portfolio to target 2% alpha or % alpha per annum, minimizing perhaps the other risk parameters? Or is it just sort of open-ended to simply maximizing, say, information ratio only? Thanks.
A great question. So quickly, the first is the problem was constrained optimization. It's something we didn't mention. This is optimization under constraint that we are solving, which definitely doesn't have a closed form solution. But even in the case of a closed form solution, you actually can't, it's not in the case where you don't have any constraints, it's not a closed form solution. But in this case, it was worse because there isn't, we have additional constraints, which makes it infeasible to solve. So that's the one. And then the other question the objective function, yes. So the objective function in this case was the quadratic utility. So the input into the model, so you get to choose what level of risk aversion. So it learns across different risk aversions. So for instance, if you wanted it to be conservative today, you would just simply lower the parameter and it would know how to change the allocation. So it learns across different levels of risk tolerance. The objective function itself is up to you. In this case, we just chose the quadratic one, which is the Markovitz standard. But it's really up to you.
Okay, I'm gonna Okay, so we're going to have that be the last question. If there are any questions that we don't get to during the session, can I ask that you approach the speakers individually if you want to engage a little bit more, because I want to give you time to walk to your next room. So we can take your question.
Cool. Thanks so much for the presentation. This could be potentially just my misunderstanding, but I'm missing the so what. So you're using 2 years worth of data, which is not a lot. Does this supplement an analyst's understanding of the sectors? Does this feed into tactical asset allocation? In that case, should we use a rolling period methodology to make this more robust and move forward? And I guess how the sparsity of data is perhaps something, because if we are using annual reports from 125 companies, even though it's 2 years, it's essentially 250 pieces of information where you only have 2 data points from each company. So maybe you can explain the so what to me a little better.
So I think, first of all, this sort of is a demonstration of concept. And as Vince mentioned, definitely while we sort of did use, annual reporting, which is sparse in its, availability and delivery, it can definitely be supplemented with more frequent information with different lenses, so on and so forth. And the end goal is that it would supplement an analyst's view. The idea is that, it's scalable across, a broad instrument universe, and we're not aiming to replace a research analyst whatsoever. It's becoming more of a research assistant in this case to speed around turnaround times and get a more accurate and representative view of risk.
I've been cut off, but thank you for the session, very insightful. We can close it and move on to the next session. If you've got questions, please reach out to them. Thanks a lot, gentlemen.